Okay, welcome back. So test two. Kind of an abrupt way to start off after spring break, but sorry about that. Will be today, this afternoon. I'm kidding. Will be. Pull up the little calendar here. We will basically have everything finished this week. I want you to have a little bit of homework on it. So our next test is going to be March 31st. And that'll be in Latin. So it'll be the same format where if you want to start early, let me know and I'll let you start early. If you need to go late, that's also perfectly fine. The material will start with what? Basically finding voltage differences. So it's going to start with delta V, the definition of delta V being the delta U over Q, and it's going to end with RC circuits. RC circuits and capacitors. I'm not sure if I'll do this next or capacitors, but it's basically once we're done with all the capacitors and resistor stuff, that'll mark the end of it. And then after that, then we start magnetic fields. And so the magnetic fields is going to be just like the first test, except basically wherever we had a B or an electric field, we're going to have a B. And because B is going to be magnetic fields, and then everything's going to fall through. And then you didn't know about physics 1 and physics 2. You're all set for life. The other thing I should mention is on either Thursday or Friday, the schedule for the fall goes live, or at least that's what our secretary says. So if any of you are thinking about doing like a double major or minor in physics, I hope you all are, or just thinking more physics, you might want to actually think about that in your schedule. And what would be going on, what you'd be eligible to take would be optics. And so with optics, what we do with that is optics uses a lot of advanced Calc 3. So in your Calc 3 class, you're going to be getting basically the divergence theorem and Stokes theorem pretty soon. And what I do is I actually start the class with that, but I assume you don't know anything about the Stokes theorem or the divergence theorem. So even though you do, okay. So I rederive them because that's one of those things you can't really see enough in life. And then what I do is I use take Maxwell's equations in integral form and show them how you can write them in differential form. So in other words, we have Gauss's law like this. Okay, once you use a little Calc 3 on it, it becomes actually, this is actually a dot, it's called a divergence. It equals that. And that's one of the differential forms of Maxwell's equations. What you can do, and actually understanding intuitively what this little symbol means here, it's called the divergence. That's a really huge part of your education. So that'd be one thing you could take. The other thing you could take is classical mechanics. And what it is this classical mechanics, but you're going to take F equals MA. And F equals MA, you're going to end up writing as d by dt, partial L with respect to Qi dot equals the partial L with respect to Qi. And it turns out that's nothing but F equals MA in a very, very abstract form. But what that allows you to do are problems you can't even begin to approach in normal physics. So in other words, let's say I gave you a hoop. Here's a hoop. And here's a pivot. So this hoop could go back and forth like that. Suppose then you have like a little marble, and this marble can then slide on the hoop like this. So the hoop can go back and forth, and then the marble can then slide on the hoop. Well, how'd you go about analyzing that situation? Okay. It turns out that with Lagrangians, you can actually look at that and actually set that up very easily. And then what you can do with that is actually really, really profound. And then you can even do other little things. You can take this point here, and then you can rotate that about this point. So you have the hoop can go back and forth and it can rotate, and the marble can go up and down along the hoop. And how do you analyze that? Also, for instance, what makes a hurricane? For a hurricane, you need a low pressure system, and the winds have to actually have a speed that actually exceeds 75 minutes for 3 minutes or more. 75 miles an hour for 3 minutes or more. The question is, well, how do you know that? Well, I'll show you how to actually calculate that. So these would be 2 courses that would be available to take in the fall if you're so interested. You do what? Yes.
Do you have office hours?
After this, I do, yes.
And do you have them also at around 1 o'clock?
1 o'clock, I do, yes. No, my Mondays are all messed up, so the Mondays are always have to think, but the answer is yes. Yeah. You only have to know the secret knock, you know, it just show up, okay? Questions? Okay, so that said, let's go on with our. Okay, again, the next test is March 31st. Let's do a little reminder of what we did last. Before break.
Can we go over on the circuit with an amp meter and what you said calculation?
Okay. Oh, the other thing, I'm glad you mentioned that. So as far as the homework goes, okay, I didn't do anything during break, which was actually mentally refreshing for me. So let's just say I'm a little bit behind in grading. So I'm going to put off your homework to, it's going to be due down on Friday, because basically I don't have enough time to get a new homework set and then solutions and so on. So you're benefiting from my being a slacker over break. So the homework is not due on Friday. So in a case like that, do you have that homework one here?
Yeah. It's honestly the first letter thing.
Yep. Okay, so this will be on homework 6, number 1. B. That up here, 5 ohms, 15 volts, 7 ohms like that. And I give you the direction of the currents. Tell you that it's I1, I tell you that this is I2, and I tell you that this reads. Ammeter reads. Amps. The question is basically find I1, I2, and V. Yep.
So because it's given, they have to join at
Exactly.
that point.
Good. So what do you know about the current? This current here has to be what then?
I1 plus I2.
Exactly. But what does I1 and I2 have to equal then?
I question. Yeah.
How come? If you have an ammeter here, what's this ammeter reading?
2 amps.
2 amps. So you get actually one equation here. So you get I1 plus I2 equals 2.
Can you leave the A out?
Well, that's just the units. You normally, I would, with any type of a unit in the equation, I'd always leave it out. And there's a reason why. Why may I not read it like that? It's not wrong, but why may I not leave it like that?
Would you have to put A's on that?
Well, they're variables. Just don't, I'm talking, just turn off your brain and think. Just kind of more basic. Okay. Well, what is A? See, that's the problem. A is not a variable. What is it? It's a unit. Okay, so this is actually 2 amps. So that A there is irrelevant. So the problem with leaving like a unit in there is that actually you can actually start thinking it's a variable, something you have to solve for. And it's not. It's just what the quantity measures. Okay, so just from a practical point of view, I won't do that. So usually when you have equations, never put in the units. Okay. Always put at the number when you at the end when you get a number, put the units in the number, but not usually in the equation. Okay. So what do you? How do you then proceed with this? Oh, they're all in here. Okay, you want to do the positive and negatives. Okay, so we assume positive current, and positive current goes from where to where voltage wise. It always goes from a high voltage to a low voltage. So in this problem here, the I1 is going this way. So on this resistor here, what does that mean? This has to be high side, this has to be low side because the current's going this way. This has to be high, this has to be low. What about over here? The buddy here? Okay. Well, what do we know about the batteries always? That they're fixed by the chemistry. This is plus minus, minus. Okay. And then you set up your loops and Phys, you'll get your answer. look at the top one first. Okay. All make sense? I guess you two were working on this last night. Okay. Questions?
We were beefing for like 2 hours straight.
Okay. Well, you have shiny halos for working on your physics before, during the tail end of your break, okay? Questions?
If- We did have a question about this, though. Would it be possible if the battery was in front of
I
the,
mean, if it was here,
yeah.
okay.
and
What would happen if it was here? How would it change?
current going the other way?
Well, they tell you the direction of the current here. But what would happen if I took this battery here? And put it right. Here. Absolutely nothing. How come? These two are,
You see?
these are in series. Okay, what does it mean to be in series? You go from one object directly into the other object. Okay. Is this resistor and this resistor in series?
No.
One of those answers is correct. Yeah, what's preventing this resistor and this resistor from being in series? This right here. Okay, if this weren't here, then they would be in series. Okay, so when you're in series, you have to go to immediately from one object to the other object. So if there's anything intervening, no longer in series. That makes sense? Okay, well, is this resistor here and this resistor here in parallel? Are these in parallel?
Mm,
How come?
Which their ends are. Or like they're not in the same.
The answer is, I agree with you, no. But how can you tell something's in parallel?
Their ends, both their ends are touching.
Yeah, all their tops are connected with wires, and then their bottoms are connected with wires. Okay, so let's put this back where it was. It was here. Okay. Is the top of this one here connected to the top of this resistor here?
Mm,
Yeah, I'm going from here directly to here. So their tops are connected.
Even if the current doesn't pass.
That doesn't matter. We're only looking at the wires connecting the tops. Now, are their bottoms connected?
No.
How come? What's messing up them being in parallel?
Batteries.
This battery, this battery. So this bottom here does not go directly to this over here. It's broken up because of this phone, and it's broken up because of this phone. That makes sense? Question?
The branch in the middle doesn't affect the being in parallel or not.
Okay, so is this one here and parallel with this one here? I mean, does not affect the parallel nature of it. So what messes this one from being in parallel with this is this battery and this battery. If that battery were not here and this battery were not here, in other words, that's so we have this. We have that, and this bottom here would go directly to that here, then they would be in parallel. Okay. Problem is that we're the battery here, and then we have the battery. Okay. That makes sense? What about this one here? Are these two in parallel? Because
Battery.
battery here as well. Okay. That makes sense. So not everything is necessarily in parallel or series. You can sometimes you'd have to keep. Okay. Questions? That said, let's try another little circuit. Let's leave this guy here.
In the equation.
No, how come? Okay, ideally, okay, we're gonna have this in lab today. So we have an ammeter here. And we have a voltmeter here. What happens if we have an ideal ammeter and an ideal voltmeter?
Don't have,
Yeah, how do you have to work? If I want to know let's say I want to measure the current in this resistor right here. Let's give these some names. So I'll make this 2, I'll make this 4, I'll make this 3. Make this 2 volts, I'll make this 3 volts. I'll make this. Okay, suppose I want the current going through this 3 ohm resistor here. Where would I have to put this ammeter?
You don't figure out which way to go.
No.
So,
Okay, what do you mean next to it? I mean, put it here? Okay, so can I do this? Why would that be really, really bad? Okay, let's figure out why. So first of all, whenever you have an ammeter, ammeters have to be placed in series. These have to be in series. Okay, this right here, if I put the ammeter here, this ammeter would be in parallel. So put it in series. Take it out here. So we're gonna have to put it right in here in series. I could put it here, or I could put it up here, or I could put it right here. Could I put it here? Anywhere along this part here, I'm gonna get the exact same value here. How come?
I think so, you gets interrupted because of the battery.
No, the current's always gonna be the same. So any current going into this battery here, it's gonna be the same as the current going out of this battery. If it were different, then somehow this would be storing current, it would be storing charge. Okay, so anywhere along here, whenever you have things in series, the current is always the same for anything in series. So I could put it here, I could put it here, I could put it here, I could put it here. If I put it here, would that be measuring the current? No, because then it gets all messed up because of this junction. So anything along here. So what would have to be the internal resistance for it if I had a perfect ammeter? Yeah, you want this to have actually 0 resistance here. How come? Because if it had a high resistance, what would happen? I'd be changing the current then going through here. And I want to measure the current going through here. And so ideally, I want this ammeter to have no resistance. Now they always have some. But you want, in an ammeter, you want the internal resistance to be as low as possible. If you could have an ideal one, you'd want 0 resistance. So sometimes people have these really, really high-end ammeters that cost like $1 bazillion. Part of the reasons why they cost $1 bazillion is that they have a very, very low internal resistance. Then they can also measure a very wide range of current values. So that said, why don't I do this? Why does this have bad written all over it? If I do this, what have I done to these 2 objects here? I place them in parallel. Why are they in parallel? Tops here are connected like this, and then their bottoms here are connected. Okay, that makes them in parallel. Now, what did we say about what's generically, if you connect a whole bunch of things in parallel, what do I know about the equivalent resistance of this whole combination? Sure, more?
1 over EQ equals 1 over.
Yeah, so you have the 1 over REQ. 1 over R the ammeter. It's 1 over R of the, I'll just say 1 over 3. But we said something else. When you have a whole bunch of things in parallel.
Equivalent has to be lower than the smallest amount.
Exactly. Whenever you have things in parallel, the resistance of the equivalent is always lower than the smallest resistance in the combination. So this resistance here has to be much lower than the ammeter. The ammeter has a resistance of very, very small, ideally 0. So you have to have something smaller than that. So now, so what am I doing to the effective resistance of this whole thing here? I'm reducing it, which means what? If I have smaller resistance here, I'm actually going to change the current going through this. And also what's going to happen is that current, when it comes this way, it's going to primarily go through the ammeter, and it's going to blow that ammeter. And these are fuse protected, so that'll happen. So today, what we're going to do, we're just going to practice putting ammeters and measuring current and measuring voltages. It's not a hard lab, but at some point, I think the only way you can learn how to use an ammeter is somebody just has to sit down and say, do the following. Otherwise, I don't think you can really learn. It's like driving a car. At some point, you just have to get behind the wheel and drive. That's so you can go to all the little classes you want, but at some point, you just have to drive the damn car. If you don't, you're not gonna know how the thing works. Okay, that makes sense? So let's go back, now let's talk about our friend, the voltmeter. So this is in series and ideally zero internal resistance. Okay, what do you have to do then with the voltmeter? These? Yeah, because they measure a voltage difference. So you're based on the voltage between here and here. So a voltmeter, you actually have to place it like this. Okay? You have to put it in parallel. So if I have current coming this way here, I have current coming this way here. When it hits this junction, what don't I really want to have happen? I don't want it to split, right? Because if it splits, then I'm changing the current going through here. So ideally, what would I want the voltage on this ammeter this voltmeter to be? As high as possible, hopefully infinite. So what you'd want to do is that for the voltmeter here, it has to be placed in parallel. Okay. I mean, ideally, have infinite resistance, infinite internal resistance. So that current comes here, very, very little that current goes through the voltmeter. So it's not really changing what I'm measuring. That makes sense? So again, if you were purchase a really, really high-end voltmeter, what it's probably going to have is an extremely high internal resistance. And then also be able to do probably a wide range of flow. Okay. That makes sense. So that said, let's go back to this problem here. And let's actually figure, I want you to find the current in each of the branches. So it helps to find the current in each of the branches. Okay, let's see how much you remember from pre-break. And on the exam, some of you may know more sophisticated ways to deal with this, like loop rule. I mean, your nodal currents and stuff like this. I don't want you to use these. I only want Kirchhoff's laws on these problems. If you give me some other method, I'm going to give you a 0 for it. Then eventually I get like electrical engineers who do something kind of clever, saying, here's the answer. That's completely correct, 0. Because I want you to do Kirchhoff's laws, because it's testing fundamental physics. I said that for you.
That's so tragic.
So,
That is so tragic.
Start by drawing.
Direction of the back, like the.
yeah, you have to come up with the direction of the current. Now, do we know how the current goes? No. Now, what's the nice thing about it? It doesn't matter. You just pick a direction and then those signs will tell you whether you're right or wrong. So where do okay, again, you don't have to do it like I do it, but do it like I do it, because I think it's more systematic. Where do I always start these things?
The batteries.
Well, I always start on the left, and then I go to the right. So I'm going to start in this branch right here, and I don't know what the current is, so what will I call the first unknown current? I1. I usually make it go clockwise for absolutely no good reason. Yes.
A branch is considered.
Okay, so how many branches would there be here? 3. So basically, it's sections in series. So this is one branch, right?
Just basically.
This is another branch, and then this is another branch. Okay, so basically anything that, as long as you go along and it's all in series, that'll be a branch. As soon as you hit a junction, you no longer have a branch. Okay, so I'm going to call this current here, and I'm going to call this here I1. So I1 hits this junction here, and what can happen at the junction? It's split or join. It doesn't matter which one do you want to have happen. Split. Do you want to split diagonally or split to the right? To the right. Okay. So if I call that current there going to the right, it's a split current, what would that then have to be? That would have to be I2. Now, this is one unknown current, so I'm going to always take the unknown current to be coming out. What do I know about this current here? That this current plus this current has to equal this current, because what goes into a junction has to equal what goes out of the junction. So what does this current here have to be such that this current plus this current equals that current? Yeah, this would have to be I1 minus I2. Because these are both coming out, so if I take I1 minus I2. And add to I2, the I2's cancel, giving me I1. I1 is what's going into that junction, right? So the current going in, the current going out. Again, if you look at electrical engineering books, they often have called this K, I think it's KCL. Okay, so this would be the Kirchhoff current law. And it just means what goes in is what goes out. A lot of books will call this I3, then they'll say I1 equals I2 plus I3. I don't like doing any of that. I think it actually makes it like more complicated.
Would you want to get points off though? for doing
No, it's just I go ahead. I'm just, you get it outgrown and I grade it, but I won't do anything about it.
that?
Am I right? Okay. Now what's the next step? And do this next step. Always label your currents of your resistors, which are positive and which are negative sides of them. So we always assume positive current, and positive current goes from a high voltage to a low voltage. So in this little resistor here, what is positive, what is negative? Yeah, this has to be positive, this has to be negative, and this little resistor here. Yeah, because the current's going this way, so this has to be a high voltage, this has to be low, a little buddy here. Going this way, so it always goes from high to low, positive, negative. Okay, so how many unknowns do we have? 2. I want to, let's do the batteries. The batteries are fixed by the chemistry. So we have 2 unknowns, I1 and I2. So how many equations do we need? We need 2. So how many and by a loop, I mean a closed loop. How many closed loops do I have in this? I have 3. I can have this little loop, or then the big loop here. Okay, it doesn't matter which loops you have. Okay, so give me a loop. Bottom triangle, clockwise or counterclockwise. Okay, so I'll start here. So I'll call this loop number 1.
Why did you start there?
Because I just always do. Okay, I could have started anywhere and I'm going to get the exact same answer. Okay, so I'm going to start loop 1 here. And I'm going to put like a little thing like that, just to indicate that I'm going clockwise here. So I hop across this battery here. If I hop across the battery, do I have a voltage gain or a voltage loss?
Loss. Okay, because you're going low from low to high.
That makes sense? You're going from the low voltage, the minus, to plus, so that's the voltage gain. So that's going to be a 2. Don't put a 2V in there because don't put it in any units. So I hop across here, that's the voltage gain. Now I come here, now I hop across my little 4 ohm resistor. Is that a gain or a loss? Because I'm going from high to low. So this is minus 4 what? I don't know. What's the current going through here? I1 minus I2, so V equals IR. So here's my R, I need here's my R. I need the I going through here. And this would be I1 minus I2. So this is just V equals IR. I hop across my battery, friend.
Minus 3.
And I'm going from a high voltage to a low, so that's going to be a minus 3. Come down here, now I hop across my 3 ohm friend. What do I get?
3.
Minus 3, I1. Okay, and again, I get that a lot. Tell me what a very common mistake is, and I always think up the generic minus 1. Yeah, don't have an equation just sitting out there not equaling something. It'd be like saying 5 plus 3y. So 5 plus 3y equals 2. 3, just you don't have a random equation. Okay, equals 0. Okay, probably beat on that a little bit more. What would I do? Yeah, get all the like terms together. So let's do the constant. What?
Is that a column or is that I1?
This is I1.
Oh.
Yeah. Okay. Because that's the current going through this part. All this right here is all. This is all I1. Okay. So what's my overall constant for that one?
-1.
Everyone agree? I have a 2. I have a minus 3. That's a minus 1. How many I1s do I have?
-7.
Oh, this is gonna be awful. Yeah, this is gonna be minus 7. Sorry about that. How many I2s? Plus 4 I2.
Could we move the 1 over early? We always want to keep it 0.
It doesn't matter where it goes. Eventually, I probably would put it to the other side. Okay. But right now, just keep it like this before doing any manipulation. So this right here is my one equation. That's as much as I can do with it. Now I need a second equation. Give me a second equation.
The whole loop.
The whole loop. Okay, I'll start here. No, I can start with the same. No, I'll start here. No, I'll start here. And with number 2. This is going to be my number 2. Okay, so I hop across my voltage, my battery. What do I get again? 2. Now I hop across my 2 ohm resistor front. What do I get? I'm going from a high to a low, so it's a voltage loss. What's the current going through there? I2. So V equals IR, so I have minus 2I2. I hop across my 4 ohm my 4 volt friend. And we have a plus or minus. This is minus 4. Then I hop across my 3 ohm friend. Minus 3. That equals 0. Okay, this one, what happens? I can I'll get a minus 2, minus 3I1, and minus 2I2 equaling 0. And this is all over, but that's okay. So at this point here, there is no more physics. Oh, and I didn't. When you do the voltages, what is that? If you're looking at electroengineering book, what would that be? It's not KCL. But when you do these loops, it's called K. Well, the I would be for the current, which is kind of this guy. When we do this, what are we doing? We're looking at voltage gains and losses. So this would be the Kirchhoff voltage law. So if you say KVL, it means basically the Kirchhoff voltage. Okay. So these would be 2 things if you pick up an electroengineering text. Okay, so let's just solve these here. So I'm going to take the one over here. So this is minus 7I1 plus 4I2, 1. I'll take the 2 over on this side as well. So I get the minus 3I1 plus 2I2 equaling 2. And what would I probably do? I could solve for one variable, put in the other, or I do something before I add it though. That's what I would do. I take this equation here, I multiply by 2. So then that would give me minus 6I1 minus 4I2 equal to 4. And then I'd add these 2 together. So if I add these 2 together, I get, oh, minus 13. That's good. They cancel. And then I have 5. Ooh. Okay. So this gives me I1 equals 5 minus sign over 13. Okay, what does that minus sign mean?
You chose the wrong direction.
It means I chose the wrong direction, but what would I get for a magnitude?
The same.
The same thing. That's the nice thing about these is you can't make a mistake with them. Okay, it just means we guessed the wrong direction for the current. However, when I go to actually put values in the equation, would I then make that a positive current? No, because I set everything up like this. So I have to use that same minus sign there when I use it throughout the rest of the calculation. Okay, so now how do I find then the ES?
Wait, why did we multiply that equation by 2?
Because I saw a 4I2 here, and if I multiply this by 2, then I have a minus 4I1. So I added these together here, these would cancel. Okay, so if I multiply this by 2, I get this equation. So then if I add these 2 equations here, they cancel, and they'll just give me this. Okay. Now, if we put in the values here, they're all kind of crappy. Frankly. What would I have? Well, it's crap no matter what we have. I'm going to take this, I will put this one from here. So I'd have minus 7, minus 5 over 13, sorry about that, plus 4I2, 1. Okay, this is going to hurt. Okay, so this is gonna be 35 over 13. Plus 4i2 equaling 1, 4i2 equaling 1 minus 35 over 13. Oh, that's nice. Get a common denominator here of 13. So this is gonna be what, minus 23 over 13? Equals 4i2. Oh. And divide through by the 4. Minus 23. If I multiply that by 4, what do I get? 52? Sorry about that.
Because we're in the wrong way, would you want us to do it on a test?
No, because it's perfectly fine.
Or should we just write?
No,
you
it's
know,
just,
the negatives?
just leave it like that. And then if you, all the minus sign means is that we picked the wrong direction. Now, with that said, what would then be the current through this branch here?
It would be joining.
No, no, just, okay, how did we set it up there? We said the current going through this diagonal branch is what?
The wrong way.
Oh, we said the current going through this branch is I1 minus I2. So the current in the diagonal branch is I1 minus I2. So what do you have to put in that equation? Don't change those signs because we set it up like this. So this equation is perfectly fine, even though our currents are wrong here. So when we put in the numbers here, don't make this a positive 5 over 13. Leave it as a minus. It's going to be this minus 5 over 13 minus, and then what is your I2? I2 is, again, we guessed wrong, minus 23 over 52.
Isn't it 22?
Well, did I mess it up?
1 over 13.
Oh, right there.
Okay, I could have easily messed up the math.
No.
Wait,
35 minus 13 is 23, 22, not 20.
oh, yeah, okay.
Which one? Did I mess this up?
1 over, go up one more.
I get the 13 here.
Yep.
Oh, so this should be a 22. Thank you. And then I get some value there like that, but that's what the value there would be. Okay. Now, if I put a voltmeter here, what would that voltmeter measure? I'm gonna put a voltmeter between here. What would my voltmeter measure? Yeah. Okay, what's across here? I have the voltage across here, plus the voltage across here. Let's go through and calculate it. So if I hop across here, according to my little current way I set this up, what am I going to have? If I go from here to here, I'm going to have a voltage loss. So I would have then minus I1, I'll put the 3 there, minus 3I1. When I hop across the battery, I would then have plus 2. So I'll give these numbers. I'll call this point A. I'll call this point B. So this is going to be your VAB. What would it happen? So this will be minus a 3. My current I1 is my buddy over here. Minus 5 over 13. Plus 2. This is going to be 15 over 13 plus 2. Get a common denominator here of 13. So this is going to be 15 plus 26 all over 13. And so this is going to be what, 41 over 13. Now, is that the voltage for this branch? Is the voltage for this branch? Or is that the voltage for this branch? That's all of them. Because what do you know about this branch here? And this branch here, and this branch here? They're all in parallel. Okay, because what happens? This bottom and this top are connected to this bottom and this top, connected to this bottom and this top. So each of these branches here are all in parallel. That's all. Their tops are connected, and all their bottoms are connected. And what do you know about anything in voltage? I mean, in parallel, their voltages are the same. Okay. Make sense? Good. Okay. Now, I want to look at a really common circuit that occurs all the time. And then,
When you say, sorry.
Yep.
When you say like equal voltages, would that be like?
put a voltmeter there. So if you took a voltmeter, as you raised it up, I put it across here, that's what I'd be measuring. If I put it across here on this branch, this branch, this branch, I would get the same voltage no matter what. Because they're all in parallel.
Like if branch one was 5 and they'd all be 5, when you put it on either end, would it then be 15 or still be 5?
So which, so let's say, I'm just gonna draw something here. Okay, so if I put it here, I get 5, here I get 5, here I get 5. Now, where do you want to get the 15?
In the corners, would that be 15?
Okay,
Or would that still be?
all these wires here, doesn't matter where I put the probe, it's all the same. Okay, it's just like here. Doesn't matter where I put the probe, it gets the same. So I can put it here, I can put it here, I can put it here, put it here, put it here. No matter what, I'm gonna get 15. I mean, I'm gonna get the 5.
Okay.
How do you have to get 15? They would have to all be in series. They'd have to be in some series combination. Okay, because voltages in series add, voltages in parallel are always the same. What about current?
Opposite.
Meaning?
In series, they all add.
Oh. In series, what do you know? If I have a whole bunch of things in series,
They're all
the current going in here has to be the current going out. Anything in series has the same current. Anything in parallel, what happens? Yeah, if this current comes here and hits a junction, some current goes this way, some current goes that way, some current goes that way. If I add these currents coming out, how does it equal to the current going in? They have to be the same. So what happens is, in parallel, the currents add. In series, the currents are the same. But with the voltage, in parallel, the voltages are all the same. In series, the voltages add. Okay. Make sense? You can put anything in parallel, and their voltages are always the same. Anything in series, and the voltages always add. And they're a generic rule that are always true.
So for the calculation, you just looked at one of the branches?
I could have taken any of the branches. And I just picked that one because I picked that one for no good reason. I could have done that with any of the branches and I've gotten the exact same answer. As long as I use the currents that I got here like this, because I set it up for this. That make sense? Okay, I want to show you a circuit that's actually used quite a bit. Historically, it was used to determine the unknown resistance. So I want to talk about something called a Wheatstone bridge. No one really uses it for this purpose anymore, but the circuit itself is used a lot of places and a lot of calibration equipment. So this is a Wheatstone bridge. So this was a circuit used to determine the resistance of an unknown resistor. So let's say you had a resistor, it wasn't labeled, and you wanted to figure out what the resistance was. Well, how would you do it? Well, you'd actually use this device called a Wheatstone bridge. Okay, today, if somebody gives you a resistor and says, what's the resistance? What do you do?
Ohm meter.
Ohm meter. Okay, so no one bothers with the circuit, but the circuit design is used in a lot of places. Okay, and it's going to be this. We're going to have a battery here. It's going to come up here. There's a resistance R1. Make this the put a line through it like this. I'll explain what that line means in a second. I'll call this R2. Make this R3 here like this. And here's my Rx. This is the unknown. That, and between here, I have what's called a galvanometer. Anyone know what a galvanometer is? It's a very sensitive ammeter. So it's just an ammeter, but very sensitive. Like that. And what does it mean if you put a line through something like this? I have a resistor, but then I drew this weird arrow through it. Any electrical thing with an arrow through it means it's variable. So when you have this circuit like this, that just means a variable resistor. And these are given two different names. Kind of the big bulkier ones are called a rheostat. We'll see one later on. I don't think. No, we don't have anyone. We don't have any out right now. So they're kind of going to be big bulkier things. We'll see one of those in not the distant future. And kind of the smaller version of these things, they're called a potentiometer. And so they have about a size like this. They have a little tiny knob, and you can turn them like this. Sometimes with electronics, you get kind of like funky thing going in there. And somebody who knows what they're doing will say, "Well, I think I have to go there and thin out the pots." You know, what are you even talking about? They mean basically they have to go out there and thin out the potentiometers. Okay, so what you do here is you vary R2 until there's absolutely no current inside here. Okay, this reads 0. And then that is going to allow us to measure what Rx is. So I'll just say that in terms of words, and then we'll see how this works. So what we do is we vary R2 until the galvanometer reads 0. Okay, then we can determine Rx. And we'll see how that works next time. Okay, and that's the galvanometer. That's the whole thing here is called a Wheatstone bridge. But this idea here of having these 4 things here like this, and something in between, that's called a bridge, and that's used all the time. In fact, a variation on this, when we replace these with diodes, it's going to allow us to convert AC to DC. So later on, we're going to see how to convert AC to DC. It's going to make use of this bridge here. Okay, have a good day.